As you see in the video, every time you have like a charged particle moving in a magnetic field, we have some kind of interaction between this movement, right, the motion of the charge and the electrical field, sorry, the magnetic field, and then you are going to see some interesting phenomenon. Let's just recall what we learned when you're studying the electric field, because remember, the presence of electric charge, right, of any object with charge actually modifies the space on its surroundings, right? So, and you have the generation of the electric field, and the electric field is going to generate a force. And we remember, if you recall, that actually the force, the electric field, the force like generated by the electric field has this expression, right? We have something like this. We have the product of the charge times the electric field. So this is what we learn actually in lecture 2, right? Remember, if we go back a little bit, we can actually remember that the electric field is going to generate a force, and this force here is actually can be, you can do the opposite, right? You can consider this charge here, and then you can actually calculate the force that is going to be generated in any point of space by just multiplying the value of a charge like located at this particular point by the electrical field generated by this charge here, right? And we can actually define the the magnetic field the same way. So this is experimental fact actually. When you have like the charge moving in a magnetic field, is going to generate a force too, and this force is proportional, so I'm going to call this is proportional to the velocity of this of the particle, of the charged particle, and also the magnetic field as well. And the expression that we can prove is actually experimentally find is actually the magnetic force that is going to be generated in a particle like moving in a magnetic field is just the product between the magnitude of the charge times the vector product between the velocity of this charge and the magnetic field. Oh damn. As you can see, guys, is similar in nature, but we have some significant differences here. First of all, here when you're analyzing, right, the electric field, one main characteristic here is that actually this charge here is static, right? It's not moving, and you're analyzing the force that is generated around it. The force here, very important. Whoa. The force, the electric force generated here by the presence of this particular charge in any other charge, like within its surroundings, right? This is actually is radial. Is radial, and if you have any two part of charges, right, any two parts that you analyze is they're going to be in a line, right?
Excuse me, Professor.
Yes.
We don't see your screen.
Oh my god. 1 second. Wait. Oh my. Sorry. Can you see now? Guys, I'm just recalling, right? We're recalling the electric force. Electric force has this expression, right, that we actually studied in the second lecture. But the electric force actually is calculated, right? Is found for a charge that is actually static. The electric force is radial, and any pair of forces are in line, right? The electric force, they acts in the line that supports the two particles. This is very important things. That means every two particles that you look, for example, for the electric force, those forces are going to be in a plane, in the same plane. And this is a major difference now that we are going to analyze the magnetic forces, because the magnetic forces, let me just erase this one. Okay, the magnetic forces, first of all, the charge now is moving. Charge is moving, and one major characteristics that actually is represented by this vector product here, right? As you guys can remember from mathematics, from calculus, right? This, the vector product, the result is a vector, and is a vector that is not in the same plane. I'm going to approach this soon, but I just have to emphasize this here, that in this case here, right, the force is in a different plane. In mathematical terms, right, para forces in line, here F is the electric force is actually the force and the electric force and the electric field, they have the same direction, right? Those two, they have the same direction. This is very important. Okay, you have some major differences here, although the mathematical forms are similar, right? You have a charge multiplied by some by a vector, but they're different, clearly not the same. So let's see what is going on. And but before we studied this expression here, the expression for the magnetic force in detail, let's just recall some major aspects of the vector product, because now we have to be very careful, very careful in how we treat the this magnetic force. If you go back to high school, guys, you remember that in high school we learned a couple of techniques they call the right hand rule, right, to actually to find out the direction of the magnetic force. Whoa, I erased a mistake here. I don't know if you recall that, but there are a couple of versions of this right hand rule. The first one, let's imagine here, right, in this you have the magnetic field coming from north to south here, and I'm using magnets. I got these figures from hyperphysics. Thank you so much for that. And it's very easy actually to cover. We have different ways. Okay, let's explain this one first. All you have to do, you point your fingertips in the direction of the magnetic field. You point your thumb in the direction of the motion of the charged particle, and the palm of your hand, right? The palm of your hand is going to point the direction of the force that is going to be um, generated by the magnetic field interacting with the motion of the charged particle. In this case, right, if you have like a positive particle here, right, that is moving upwards in my, let's put one system here, maybe it's better to understand if I put the system here. So this is going, no, let's put opposite, let's put like this, let's put a reference frame here. So this is going to be X, this is going to be Y, and we have Z in kind of this plane here, going to be Z. Whoa. Okay, have like a reference frame like this. So in this case we have this the force generated here is actually pointing in the positive direction of the z axis. You can do the same using this is alternative rule, right? All you have to do, you have to actually align your fingers with the vector v, and then you curl your fingers in the direction of the b vector, of the magnetic field vector. Your thumb is going to point in the direction of the force generated by these two vectors, right? That in this case is exactly the same. Another very popular way to do that, guys, I don't know if you remember, is actually using this one. I got this figure from Wikipedia. In our case, all you have to do, we say that this is the blue vector here is going to be the velocity of the particle. So this is going to be v. This one, the middle finger, is going to be b, the magnetic field. And the resultant here of this vector product is going to be defined, is going to be indicated here by the position of your thumb. So this is the force, and this is called the right hand rule. And this is valid, this is very important to say here, this is valid for a positive particle. Okay, if you have a positive particle, this is going to be valid for positive particle. If you are considering, for example, like a negative charge, this is going to be opposite. Okay, guys? And some people teach students to use what they call the left hand rule. So instead of using this one that is right here, right now, all you have to do is considering the left. We can actually reflect this. It's going to give you, let's see, what is that? Let's see if I can maybe I can do it. We can use the, let's see, can I, oh yeah. Sorry, we can do like in this case, if you have like a negative particle, we could use like the left hand rule, but it's really up to you guys. You can use always the one of those here, for example this one, and just changing the direction at the end. Okay, but what you have to remember, and this comes from mathematics, right? You have many ways to define the vector, the direction of the vector that is resultant from the vector product operation. I think a very common one and very popular, I think first years in engineering classes, is the actually using this the determinant, right? You can just have to calculate this determinant using the unit vectors for each direction and the components, each like orthogonal components of the vectors that you want to operate the vector product. You also have the index notation that you use, like the Levi-Civita tensor. I don't know if you guys are familiar with this one, this method here. I'm going to leave here, so if you guys want to try, and I can solve some problems for you like using this notation. Particularly physicists really like this notation because it's very compact. And but for engineering in general, we use this. We define the vector product, right? Like this. We say that, for example, we make this triangle here, and you define this as positive, and if you have any product in the different, in the, for example, in the counterclockwise direction here, that is going to be negative. I'm going to show some examples how to use this. For example, here, if you are doing the vector product between I hat and j hat in this direction, right? So that clear explicitly I'm doing I hat vector product j. This is equals k hat. Okay, if you are doing the opposite direction, for example j vector product I hat, this is going to be minus k. Man, not too much space, but I'm going to do some examples here so you guys are going to be comfortable. I recommend you to use this one. I think this is a practical, very practical to use. Okay, let's see what else I have to tell you. Okay, we can try. Let's make some examples here using this notation, this technique. Let's consider here, guys, a couple of cases, like cases depicted here in items A, B, and C. And we are trying to find what is the direction of the force considering consider these dispositions here, these arrangements of velocity and magnetic fields. So for the first case, let's analyze first here the case illustrated in item A. For this case, guys, I have that the velocity, right, is going to be minus v, right, is going in this direction, minus v, the magnitude of velocity, I. Let's make colorful so it's easier to see the pattern here. And the magnetic field B is going to be the magnitude of this the magnetic field times, oh, this is going to be minus, sorry, minus in the minus j direction. If you see, we don't have to calculate everything. The charge is positive, right? Let's start just by calculating the vector product between the velocity and the magnetic field. So we have v vector product b. This is going to be vb I vector product j. Let's copy from here to make things faster. So this is going to be I vector product j, and according here to our convention, right, if I'm multiplying in the clockwise direction, the result is going to be k. So the result here is going to be k hat, positive k hat. So that means that the force acting there, you can actually write the force. The magnetic force is going to be the value of this charge that is positive, is one is electron, sorry, it's a positive charge here, I don't know, a proton, and then times v times b, and in the k, positive k direction. So this is a very important result. If we wanna, not if, we have to, it's better to represent this right there. Maybe let's put another color here. Let's put this. Okay, let's put these colors here. And you have actually the force, the magnetic force is pointing. Let's make a little bit thicker. The magnetic force is pointing in this direction. We can use the right hand rule, right, to see that too. If you put, man, I'm terrible in doing this kind of drawing. If you uh, pointing finger here, this is going to be middle finger, and thumb would be here somewhere. My god, sorry. So but I want you guys to remember that you can actually use the right hand rule here, any one of them. You can use actually point your fingers here and thumb here, so that means that the force is going to be this direction, right? The same, doesn't matter. But here you can use, clearly you can use to check if this is right, you can use the right hand rule, any one of the three versions that we studied there, I mentioned before and I showed you. So let's go to the second case here, guys. We have in this case here, let's describe this, guys. We have this, the velocity here is going to be minus v j. I'm going to lose the colors for now, but I'm going to leave colored in your on your notes. The vector b is going to be minus b k hat. So if we do this vector product here, we are going to find that actually this is going to be v times the magnitude of the velocity times the magnitude of the magnetic field times j vector product j hat with k hat, and this is in this direction, so the result is going to be I hat. So the result here is going to be I hat. But now when you're writing the force, you have to remember that actually this here is on a charge with negative charge, so that means that this force here is going to be minus. I have to change the sign, so this is going to be QVB, and this one is going to be in the minus I had. Okay, again guys, we can actually, just a second here, let me put this. We can also use here the left hand rule to determine the direction. Also is one alternative. You have to see that actually this magnetic force here is pointing left in our drawings here. This is actually pointing, oh man, this is bad, a bit thicker so you guys can see properly. Let me see, this one maybe better. So this is pointing this direction. Again, as I told you, as I mentioned before, you can actually use the left hand rule to do that, yeah, to find this direction. So this is the magnetic force. And in this case here, guys, the last case, as you can see, both the velocity and the magnetic field have the same direction. Just the in this case, you can see that actually the vector product is going to be 0. So this is going to be V minus Vj, and the magnetic field is going to be Bj, and then this product here is going to be, the vector product is going to be 0. Just to remember you have to remember that if you do the vector product, what the hell is going on here? Sorry, just a small problem with my tablet here. If you have vector product between vectors that are parallel, this is going to be 0 always. So that means that if you have this kind of product here, vector product between parallel vectors, this is going to be 0. Going to be the 0 vector. Just as a reminder here. This is going to be 0, guys. So you don't have to worry about. And this is actually easier to see if you go back here to the previous, to our formula, right? Is actually what we learn in high school. Of course, in high school we don't learn the magnetic force like in this form, right? In the vector product form, we learn that actually the magnetic force is going to be the product between the charge, the magnitude of velocity, magnitude of the magnetic field, times the sine of the angle between, I don't know if you use theta or something, between these two. I think you are in the textbook, this is phi, so I'm going to put phi. So that is phi, meaning the angle between the velocity and the magnetic field. So this is actually the expression that we learn in high school. Okay, let's go back here, guys. This is easier, I think. If you have this kind of problems here, I'm going to solve one problem, but for the time being, I would like to stop here just for a little bit. So did you understand until now? I think this is, if it's, is it clear enough for you guys? The parallels between the forces and how to calculate and what represents everything. And I'm going to solve one simple example here on how actually to operate when you have proper vectors in three dimensions.